Hi, in this video we're going to continue our study of the systematic treatment of equilibrium. In the first video we went over how to set up the system of equations by looking at the reactions that are going on in your system. And so if you haven't watched that yet, I encourage you to go back and watch it first. I've dropped the link in the description below. The other reason you need to watch that is because we are continuing with the same problems we used in that video. And so if you haven't watched that video, you won't know where the equations I'm using came from in the first place. Again, when we get to the beginning of this video, we've basically set up our systems of equations, and now what we want to do is we want to solve those systems of equations to find the concentrations of the species in our system. So let's talk about how to solve a system of equations. And the rules I'm going to give you will work for any system of equations, not just ones related to the systematic treatment of equilibrium. And basically the first thing you need to do is you need to find an unknown to use as your target unknown. I don't know if that's the actual term for it. It's the term I use when I'm thinking about this. But basically what you want when you're doing this, you can technically choose any unknown in your system, but it's always easiest if you use an unknown that has two distinct characteristics. First of all, it should be in as many equations as possible. Second of all, in your system, it should be a fairly important chemical species. So relatively speaking, there should be a lot of it. And so we'll talk through target selection a little more as we look at our two different systems. The second thing is to pick one equation to use as the base equation, which eventually you're going to use to solve for your target unknown concentration. And so the point of picking this equation is you want to set it aside from all the other equations. Let me tell you, if you use an equation twice in this solving process, everything will sort of fall apart and you'll say, well, it all just disappeared. You have to only use each equation once. So the thing is to identify which sort of equation is going to be the best one to use to solve for your unknown later. And that's what we're doing in step 2. Now, generally speaking, what I do is I look for something that has multiplication or division, like a fraction in it, because those tend to be the worst ones to use in step 3. I don't know if that makes sense. So I just take whichever one I think is appropriate and I put it aside. You can technically use any equation as your base. You'll get better and better as you do more and more of these problems at picking out which one is the best one to set aside for later. So the third step is to take your non-base equations, basically the ones you didn't set aside earlier, and you're going to rewrite all your other unknowns, the ones that aren't your target unknown, in terms of the target unknown concentration. Once you do that, you should have terms for everything else. In terms of your unknown, you can take those expressions, plug them into your base equation, and then that will give you an equation that's just got the concentration of your target unknown and nothing else, and then you can solve for your target unknown. And then once you have that, you can easily solve for your other unknowns. This all sounds pretty pedantic right now because we're not actually applying it to a problem. I'm going to go ahead and start with the first example that we used in our last video, which is basically taking half a mole of pure acetic acid and diluting it to 1 liter with water. So we now have an aqueous solution of acetic acid. And so what we're going to do here is we're going to find the concentrations of all the species in the system. In the last video, we had identified 4 different unknowns: OH minus concentration, H plus concentration, acetic acid concentration, and then the conjugate base or acetate concentration. So those are the 4 that we're trying to identify here. And then we'd also, for those 4 unknowns, come up with a system of 4 different equations, which I have listed over here on the right. We need to first pick our target unknown, and I'm just going to say straight off that H plus would be a good one here. And the reason I pick H plus is, again, 2 reasons. First of all, it appears in 3 out of the 4 equations. Now, it is not the only one that does that. Also, acetate does as well. But also, I know that the H plus concentration is going to be relatively important in this solution. And the reason I say that is because this is an acidic solution. I know it's going to have a lot of H plus. So now we're going to pick our base equation. Now remember, everything that's not the base equation, we're going to use to solve for other concentrations in terms of the unknown concentration. For me, that's easiest to do if, number one, I don't have many variables, or number two, we're adding and subtracting instead of dividing and multiplying. So when I look at these, I see that equation number 2 only has 2 variables, which is great. I'm not going to use that as the base equation. I also see that equations 1 and 3, we're just adding stuff. And so I'm not going to use those as the base equation. That means that equation 4 is going to be the base equation. I'm sliding that down to the bottom so we don't use it in our future calculations yet. All right, in step 3, we're going to use the other equations to write our other unknowns, and so that would be OH minus, acetic acid, and acetate concentrations in terms of the concentration of our target unknown, which is H plus. So when I look at this, the first thing I see that's pretty easy is I see equation 2, and you could see that H plus times OH minus equals 10 to the minus 14th. So that has the H plus concentration in it. It also has the OH minus concentration in it, and we're going to solve for OH minus in terms of H plus. So we're going to divide both sides by H plus, and we get OH minus equals 10 to the minus 14th divided by H plus concentration. The next thing I want to look at is I want to look at equation 1. In equation 1, which was our charge balance equation, we had OH minus concentration plus acetate concentration equals H plus. Well, we already know what our OH minus concentration is in terms of H plus. We don't know what our acetate concentration is in terms of H plus. So let's solve for our acetate concentration in terms of everything else. And what we get is the acetate concentration equaling to H plus concentration minus OH minus concentration. Well, we know what the OH minus concentration is in terms of H plus, and so we're going to plug in 10 to the minus 14th divided by H plus concentration there for OH minus, and now we have a concentration for acetate in terms of just H plus. The final equation, equation 3, was our mass balance equation, where we had the total amount of acetic acid species, in other words, protonated acetic acid plus the acetate equals the total amount we put in originally, 0.5 molar. And so what we're going to do now is we're going to solve that for acetic acid, not for acetate, because we already know the concentration for acetate in terms of H plus. And so we get this expression, and we're going to take the expression we derived for acetate earlier, we're going to plug that in for the acetate concentration. And yeah, that looks a little messy. That concludes step 3. We now have 3 different equations for each of our 3 non-target unknowns that describe their concentration in terms of the H plus concentration. So we are good so far. So now we go to step 4. And in step 4, we're going to substitute those expressions we derived in step 3 into the base equation. And so if you look at what's in the base equation, we have the H plus concentration, which we're solving for eventually. So we're going to leave that there. And then we have the acetate concentration. And so we're going to plug in our expression for acetate in terms of H plus. And then on the bottom, we have our acetic acid concentration. And we're going to take the expression we just derived for acetic acid in terms of H plus, and we're going to plug that in there. So when we do that, we get this monster of a thing, and now we get to solve for our target unknown. Now, when you look at this, this looks like a hot mess. You have a fraction with fractions in the numerator and fractions in the denominator, and it's possible to multiply through by things and get rid of the fractions in the numerator and the denominator, so you just have the main fraction, but then you basically end up with a cubic. You're going to have x cubed plus something x squared plus something x plus something, and those are not always easy to solve for. So at this point, we come down to picking one of the 2 ways to solve. And in general, the 2 ways you can solve this are first approximate to simplify, and that's what we're going to be doing in this video. And the second is to use computational tools. So what we're going to do is we're going to make some approximations. The approximation we're going to make regards OH minus. OH minus is going to be very small in comparison to everything else. And so if you're adding it or subtracting it from anything else, just ignore that. The reason I say that is because we are in an acidic solution and we know we're going to have a lot of H plus, and that means by definition we're going to have a very small amount of OH minus. Again, this is an assumption. Anytime you make an assumption, you have to check that assumption after you've solved for all your concentrations and see if it was a good assumption. If not, you have to go back and figure out a different assumption. But if OH minus is tiny, then if you look at this expression right here, H plus minus, well, this used to be OH minus. OH minus was really tiny, so H plus minus something really tiny is just going to be approximately H plus. So we can cross out that. And again, we have the same sort of thing in the bottom, so we can cross out that as well. And that simplifies it quite a bit because we basically end up with H plus squared on the top and 0.5 molar minus H plus on the bottom. And now we can start doing some algebra. We have a quadratic equation and we know how to solve that very easily. So again, here's our thing. We want to get rid of the fraction, so let's multiply both sides by 0.5 molar minus H plus. And what we get is H plus squared equals this. And let's multiply that out, move everything over to one side, and we end up with this equation. Now we have a quadratic equation in the form ax squared plus bx plus c equals 0, and so we can plug what we know into the quadratic equation. Here our a value is 1, b equals 1.75 times 10 to the minus 5th, and c equals 8.75 times 10 to the minus 6th. So the quadratic equation says x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So we're going to plug in those numbers there. And now I'm going to simplify it. I'm basically taking everything under the square root symbol, and I'm just going to combine that all into one number. And now it's pretty easy to solve for our two values for H plus. And if you look at those, you can see that one of them is negative. You can't have a negative concentration, so we can throw that out. And it turns out our H plus concentration is going to be 2.94 times 10 to the minus 3rd. So with an H plus concentration of 2.94 times 10 to the minus 3rd, now we can move on to step 6. In step 6, we are going to take that value for H plus and we're going to plug it into the expressions we derived in step 3 with all these concentrations in terms of H plus. Oh, hello, cat. The cat is going to tell you about these concentrations. So I think the OH minus concentration is easiest to solve for. It's going to be 10 to the minus 14th divided by our H plus concentration, which is going to be 3.4 times 10 to the minus 12th. Our acetate concentration is going to be H plus basically minus OH minus. And so we're going to have 2.94 times 10 to the minus 3rd minus 3.4 times 10 to the minus 12th, which is basically 2.94 times 10 to the minus 3rd. Now you'll notice here that the approximation we made was that acetate was approximately equal to H plus minus something that didn't even count. And you'll see that's what actually happened here. Here we have our acetate concentration approximately equaling the H plus concentration. Now if you look at equation 3, you can see that acetic acid concentration is supposed to be 0.5 molar minus essentially the acetate concentration, right? Because that's what that is. And so we can take 0.5 molar, subtract 2.94 times 10 to the minus 3rd, and our acetic acid concentration is going to be 0.497. Here are the concentrations that we just calculated. It's always good to look at this and ask, does this make sense? Acetic acid is a weak acid. It doesn't dissociate very much. And therefore, the acetic acid concentration should be much higher than the acetate concentration. And of course, our OH minus concentration is much less than the H plus concentration, as we said earlier. So that all looks good. We have solved that for all of our species. But now we're going to go to our more complicated system. This is the system in which we took 0.1 molar sodium bicarbonate, baking soda. We dissolved it in a liter of water, and we had 6 unknowns now. We have OH minus, we have sodium, we have H plus, we have bicarbonate, carbonate, and carbonic acid. So 6 different unknowns. And we have our 6 equations that we're going to use to solve for those 6 unknowns. Now, I say there are 6 unknowns, but there actually aren't. When we were going through and doing these, we figured out that sodium was 0.1 molar, and that is one of our equations. So we really only are solving for 5 unknowns here because we know the sodium. So for my target unknown, I'm going to pick bicarbonate. Now, I could pick H+, since H+ appears in a lot of these equations, basically the same number that bicarbonate does. The reason I'm not picking it is because I know that sodium bicarbonate is a base. And that tells me H+ is going to be fairly small. And it's easiest to work with something that is not going to be terribly small. Now we need to pick our base equation that we're going to work towards. And you'll notice that a lot of these are fairly simple, but there are a couple that look kind of hairy, and those are these 2. And I'm actually going to pick both of those for now, and I'll show you what I'm going to do with that in the future. But that tells me that what I'm going to do is take these first 4, and I'm going to use those to solve for as many of the unknown equations as possible. So let's go ahead and let's start doing that. I already said that sodium is known. It's not really an unknown, so I'm going to ignore that. To do the rest, I'm going to make some assumptions. So I'm going to make the assumptions before we start calculating everything out. The first assumption, and this isn't an assumption, I know that bicarbonate is mildly basic. And I knew this even before I went to grad school because I used to make baking soda volcanoes with my kids. It's a base, and you can throw any acid in there. It will react with the acid to give you that bubbly solution. Because I know it's mildly basic, I know that the H+ concentration is going to be very small, and it's probably going to be much, much smaller than Na+, because the Na+ concentration is 0.1. If you had an H+ concentration of 0.1, that would give you a pH of 1. It would be extremely acidic, so that's not happening. H+ concentration is going to be much, much smaller than Na+. The OH- concentration is also going to be small. Now, this one is a little harder to figure out, but again, I'm assuming this because I know bicarbonate solution is only a little bit basic. I don't remember what the pH of these bicarbonate solutions are, but I think they're somewhere in the 8 to 9 range. Okay, so OH- will be a little bit bigger than H+, but it's not going to be hugely bigger. The reason these help is because when we look at our charge balance equation that we generated in the first video, we can say, hey, OH- is really tiny. When we add it to something, it's as though we're adding nothing. So let's get that out. H+ concentration is going to be really tiny compared to these other things. So when we add H+ to the other things, it's as though we're adding nothing. And that simplifies things quite a bit. So now we only have 3 unknowns, except one of them is not actually unknown. It's our Na+ concentration, which we do know, that's 0.1. And that gives us basically 2 unknowns, the bicarbonate concentration and the carbonate concentration. And we want to solve for the carbonate concentration in terms of bicarbonate. We solve for carbonate, we simplify this down, and we get this. Let's look at another equation that we generated, which is our mass balance equation for the carbonic acid species. So our carbonic acid concentration plus our bicarbonate concentration plus our carbonate concentration is going to equal 0.1, which is the total amount of carbonate species we put in at the beginning. Now, we just calculated that the carbonate concentration is going to be this in terms of bicarbonate. So let's go ahead and plug that in. And now we can solve for carbonic acid in terms of bicarbonate. And you can see that we can simplify this down a little more. And we get this, which you'll notice is exactly the same as the expression we derived for the carbonate concentration. Now at this point, now that we have our bicarbonate and our carbonate expressions, I'm going to take the base equations, which are basically our Ka expressions, and I'm going to rearrange them so that we have H plus on one side and everything else on the other. For the first Ka, that would look like this. For the second Ka, that would look like that. And you can see that this is H plus in terms of bicarbonate and one other thing. The equation on the left is in terms of bicarbonate and carbonic acid. The equation on the right is bicarbonate and carbonate. And we have expressions for those in terms of bicarbonate. So the one for carbonic acid looks like this. We can rearrange it. So H plus looks like this. The Ka2 expression, we've got carbonate in there. Carbonate concentration equals this in terms of bicarbonate. And then H plus is going to look like this. And then since these both equal H plus, this equals that. And so we can set those two expressions equal to each other because they're both equal to H plus. And now we have an equation that's just bicarbonate and constants and nothing else. And so now we can solve for bicarbonate. Let's do that. Now we get to solve for our target unknown. And the way I'm going to do this first is to cross multiply here. And we end up with this expression. And you'll see there's things that are squared on either side. One of them is just the bicarbonate squared. But this expression right here, let's actually multiply that out. And then we can multiply through that parentheses by 4.47 times 10 to the minus 7th. And we get this. But remember, we want it in the form ax squared plus bx plus c equals 0. So we need to move the other x squared, well, bicarbonate squared, over to this side. And I'll flip the terms around a little. And now we have it in that form. Our a is 1.1175 times 10 to the minus 7th. B is negative 2.235 times 10 to the minus 8th. Don't forget the negative. It is really important. C is 1.0707 times 10 to the minus 9th. By the way, try not to round these. I did that the first time I went through the math, and I ended up with a really tiny number that made no sense because those little tiny bits actually make a big difference. We plug it into our quadratic equation, and so our bicarbonate is going to be this mess. We're going to get 2 roots from that. I'm going to simplify everything under the square root symbol again. So we have basically negative, negative. We have 2.235 times 10 to the minus 8th plus or minus 4.574 times 10 to the minus 9th divided by 2 times 1.175 times 10 to the minus 7th. And when you do that, you get 2 roots, 0.1146 and 0.0795. Now, both of these are positive. We can't eliminate one for being negative here. So how do we know which one is correct? Remember, the initial concentration of bicarbonate was only 0.1 molar. It can't be more than 0.1 molar because where would that have come from? So it's going to have to be this one. It's going to have to be the 0.0795. Okay, so now we know 2 concentrations. We know our sodium is 0.1. We know our bicarbonate is 0.0795. So now we can solve for our other unknowns. Bicarbonate is the same as carbonate. Remember, we figured that out, which is going to be 0.05 minus 0.5 times the bicarbonate concentration, which was 0.0795. And that means they're both going to be 0.01025. H plus is going to be 4.47 times 10 to the minus 7th times the carbonic acid concentration divided by bicarbonate. So we can plug in the numbers we already know. And that gives us a concentration of 5.76 times 10 to the minus 8th. And then the last one that we don't know is OH minus. Well, we know that H plus times OH minus equals 10 to the minus 14th. So OH minus is 10 to the minus 14th divided by H plus, which gives us a concentration of 1.74 times 10 to the minus 7th. So here are the concentrations we just calculated. Let's check our assumptions. First, we assumed that the sodium bicarbonate solution will be mildly basic. And you can see that it has slightly more hydroxide than it has H plus. So that does make it mildly basic. It doesn't have a huge amount more. It's not super basic, but it is basic. That checks out. The second assumption we made was that our H plus concentration would be much, much smaller than sodium. Sodium concentration is 0.1. Our hydrogen concentration is basically 6 times 10 to the minus 8th. That's a difference of, 7 orders of magnitude almost. So that is definitely the case. And then finally, we assumed that our hydroxide concentration was much, much smaller than the bicarbonate concentration. Our bicarbonate concentration is basically, let's call that 8 times 10 to the minus 2. Our hydroxide concentration is basically 2 times 10 to the minus 7th. So you have almost 5 orders of magnitude difference there. OH minus is definitely substantially smaller than bicarbonate. The reason we do these approximations is they help us solve difficult systems of equations that we almost always tend to generate in this systematic treatment of equilibrium. Despite what you might think about that last problem, that was actually a fairly simple system to solve for. That sounds horrible, but it's true. But when you practice on the simpler problems, you start getting very good at figuring out what you can approximate away and what you can't. You may be really annoyed by that last problem, actually the first problem as well, and you might wonder, hey, can't we do this a little easier in this era of high tech? And you absolutely can. In fact, that's what our third video is going to be about. We're going to look at a couple of different tools that you can use to solve these equations. But the problem is, if you don't set them up correctly, you might get the wrong answers and you might not know. So it's always good to get an approximate idea of what you're going to expect, and that's what we're doing here. I hope this was helpful, and I look forward to seeing you again soon.